Hello? Are we alive? Did I catch anything on fire? How are you all doing this morning? We are alive? That's good. Hmm, I'm almost alive. Does that count? You're doing great this night? Let's go. Um, so, we have... I guess I should flip over to this. Since Battery has been asking for so much Glinda recently, right? I decided to indulge him. And we're going to do a short little stream today where we finish up the part of ray tracing that I didn't finish in the earlier stream. Or in other words, we're going to make Glinda look really pretty. So, to get started, we need to talk about some scary looking math. A Glinda stream just for you, you boy. So, scary looking math. We're going to talk about something called, as I forget to put the glove on. We need to put the gloves on, chat. Something called the rendering equation. It's sometimes also called the light equation. And we're just gonna write it down real fast. It says that the light outgoing at some point in some direction is equal to the light emitted at that point in that direction plus the average over a hemisphere. I'm writing down a simplified version. In the normal rendering equation, you're going to get a integral there, but the integral just says average over a hemisphere of the incoming light at that point in an incoming direction times the BRDF at that point, considering the incoming and outgoing directions, times the dot product of the incoming direction with the normal of the surface. Okay, so what the hell does that all mean? Well, this term, right, says that if the surface is a light source, right, any light that we're generating is part of the output, right? That part makes sense, right? If we are emitting light, the output light will be the light that we emitted. Okay? So then this average over a hemisphere stuff basically says, okay, I have this surface point. I want to take the hemisphere, so the half sphere, centered at that point, and I'm going to sample the light in every single direction. So omega I is going to be every single direction inside that hemisphere, every possible direction. It turns out that computers are not good at solving for every possible direction. So there's an unfortunate property of this equation. This average over hemisphere part makes it unsolvable. I can spell. which is just a mild concern, right? It's mildly concerning that this equation is unsolvable. But that's not necessarily a deal breaker. All that means is that we need to do approximations. So this implies that we have to approximate. And we will talk in a minute about what approximation means. So what are we actually computing as we do it for every direction inside of this semicircle, inside this hemisphere? Well, we're taking the light that's coming in, okay? And we're multiplying it by a bidirectional reflectance distribution function. That's a lot of really big words to say that we're multiplying it by the surface material. So we're going to take the incoming light and we're going to multiply it by the surface material. And then we're going to multiply all of that by the dot product of the incoming direction and the surface normal. So what that does, the part that does for us, is if you're looking at a surface and you're like the light is like hitting it straight on, it's going to be brighter than if you're looking at a surface and the light is like hitting it at like a really grazing angle. The light that hits here is going to be a lot darker, whereas the light that hits here is going to be a lot lighter. Does that make sense? So multiplying by the dot product of the incoming direction and the normal basically tells us how aligned the light is with the normal. And so we can get brighter areas where the light is straight on and darker areas where the light is closer to zero. Does that all make sense? The normal affects the brightness, yes. So, with all of that out of the way, we're going to start off by implementing what's called diffuse lighting. So, diffuse lighting does a couple of interesting simplifications to this process. So, in diffuse lighting, our BRDF, so our material, is a constant color called the albedo. So, albedo is an interesting measurement that most people aren't used to thinking about. Albedo is how much light gets reflected. So let's think about that definition for a second, right? How do you see things, right? Well, light gets shot by the sun, and then it bounces around a bunch of things, reflecting, and eventually it reflects into your eyes. So color is what gets reflected into your eyes. So what this means is that if a surface reflects a lot of red light, but not a lot of other light, it will look like it's red, if that makes sense. So this is basically a mask as to what the incoming colors look like, and then they get filtered through this mask to find the outgoing color, if that makes sense. So, to compute this, we're going to need to add a little bit more information to our hit record. So, the first thing that we're going to add is close the other stuff, to the hit record, the hit info, is we're going to add a color F called the albedo. So now what we can do is in our scene here, we can go out albedo equals, say, 100 for a red albedo. Although we're just going to set it to like a half gray, so 0.5 gray. And then we're going to set the ground to a slightly darker gray, so an albedo of like 0.3, so a slightly darker gray. So in this, we take the camera and we shoot the rays from the camera. So we do the opposite. Taking rays from light sources means that not a lot of rays are going to hit the camera, so why do we care about any of those rays? Instead, we're going to shoot rays from the camera, and since we're shooting rays from the camera, we're guaranteed that those rays are going to be, what's the word I'm looking for? We're guaranteed that those rays are going to be useful in some way. Yep. We're shooting rays from the camera, exactly, Bigger Ben. So, just like we implemented last time, right? Because if you remember from last black screen, the screens, is that just a code guide problem? I think that's a you need to refresh problem, correct? Is the screen black? Like screen is looking good on my visual at my preview end. So just like we implemented last time, right? We calculated a big old plane in front of the camera and we generated rays that go through that plane, right? So, we added albedo, and in our scene, we've set up the albedo. So now, how do we calculate something useful with the albedo? So, instead of returning the normal color here, what we're going to do is we're going to calculate what's called a Lambertian reflection value. So the idea with Lambertian diffuse, or diffuse in general, let's pull back out the picture. Is that when light hits a diffuse surface, so we have a diffuse surface, okay? What the light is going to do, let's draw a red light. So our incoming light is basically going to go any way it wants. It's just going to randomly bounce off. The only constraint here, right, is that random bounce has to be inside the hemisphere. So like it can't bounce like into the surface. In fact, that's called something different. That's not a reflection anymore. That's a refraction. Because the words have to be similar, you know? So we're going to implement this behavior where we get a random bounce. And what you're going to see is that this creates something that looks a lot like the average material. And I'm going to say that again for you too. What you're going to see is that this looks a lot like the average material. So it's like a not shiny kind of matte material. So let's implement it. So what we're going to do is we're going to create a vec3. So the other interesting thing here, right? Since the BRDF is constant, that means that bouncing is random. So vec3, why not simulate light as a wave, or even better, a wave and a particle? Because simulating it this way is already so expensive that it's unsolvable. So we want to make the simulation more complicated so it can be even more insolvable. Yes, we would use refraction when making clear objects, but I am not going to make any clear objects today, unfortunately. So we are not going to use refraction. I'm just going to make a diffuse and a metal. So we need a vec3 random in hemisphere. And we need a vec3 for the normal. So basically, the way we're going to define a hemisphere for this purpose is we're going to say, is the vector pointed in roughly the same direction as the normal? So we're going to make, actually, wait, do I have a random vector? I do not. So we're going to make a vec3 random unit vector. And so we're just going to return random in range 0, 1, random in range, random in range. And since I said it's a unit vector, we're going to normalize it. Okay. So now that we have a random unit vector, our random in hemisphere is going to take a random unit vector. So U is equal to a random unit vector, x3. And if the dot product of U and the normal is less than 0, so if they're not facing in the same direction, what we're going to do is we're just going to negate U. So U equals negative U. So if the vector is pointing into the surface, we're just going to point it out the other way. Okay, so now that we have our random in hemisphere, what we're going to do is we're going to go that our vec3 diffuse direction is going to be random in hemisphere with our hit normal. And then we're going to have our incoming light. So this is our omega I is going to be equal to just shooting another ray. So ray color, and our ray is going to be our hit position, and our direction is going to be the diffuse direction. So we're going to shoot another ray from wherever we hit in the random direction in the hemisphere we just decided. And whatever color we find in that direction is going to be our incoming light. So now what we're going to do is we're going to return our hit albedo times our incoming light. So we're multiplying our BRDF by our incoming light. And if you remember the inside of the rendering equation, right? So the part inside of for everything in the hemisphere was incoming light. So light at the point from W incoming times the BRDF at the point times omega incoming, omega outgoing, times omega incoming dotted with the normal. But you notice that this part has kind of magically disappeared from what we're returning. I'm not returning this multiplication by the normal. We're going to stick a pin in that idea, and we're going to see how this looks. Okay, you ready? So we've traced, and ideally, we now have the world's most grainy little ray trace, but we can clearly see that this sphere has some shadowing, right? If we give the tracer a couple more samples, we should get a slightly better result. And this is starting to look, it's very, look like an actual scene that you might render, right? It's super grainy. There's a lot of detail missing, right? But we can see the contact shadow between the two spheres. They're not just gray, they're starting to pick up some of the bluish tint from the sky. This looks like something that you might see outside in a very simple world, right? So we're now going to come back to this question of why are we not multiplying by the normal? Why does it look fine despite the fact that we're not multiplying by the normal? As you can see, where the light is hitting on the edges, right? The more grazing angles are starting to get subtly darker. So why is that? Well, the ray tracer sneaks in this multiplication by the normal in the fact that our random unit direction is going in the hemisphere. So the way that diffuse rendering works, that in a ray tracer in particular, that dot product gets baked in. So for some reason that I honestly do not fully understand the math behind, we can ignore the dot product when working with ray tracers. But what I'm going to do now is I'm going to tweak this diffuse lighting and to make it a little bit more better. So this isn't going to be a diffuse direction anymore. This is going to be a Lambertian direction. So Mr. Lambert decided that he would create a new tweak to the diffuse algorithm, right? That makes it better. People visually like Lambertian diffuse better than normal diffuse. It models the real world a little bit better in our brains. It's also slightly easier to calculate. The way we calculate it is that we take a random unit vector and we add that random unit vector to the normal. So what we're doing is instead of, let me pull back out the drawing. Is instead of that previous picture where from the point we were going out in every random direction along the hemisphere, what we're now going to do is we know the normal of the point, right? So we're going to drop a new point there, and we're going to sample everything in the sphere centered on that new point that's 1 unit off of the surface in the normal direction. So we're going to start shooting our random directions off of that point. What this buys us is that the directions are going to be biased more towards being in the normal direction. If the random direction happens to be on the positive side, we're going to be biasing towards the normal. We're just going to be shooting a ray towards the normal. Oh, hey, look, it's a John. So this biases all of the directions more towards being in the normal direction, is what winds up happening. And if we give that a quick render, we should see that it looks more visually appealing. Hi, John. Bye, John. So let's pull up a side-by-side of diffuse and Lambertian diffuse. You see that the shadows become a little bit more pronounced? And you see a little bit more of the bluish lighting on top of the sphere. This one, the coloring is a little bit more homogeneous, whereas this one, you get bands of like lighter color on the top and darker color at the bottom. Does that make sense? So now I mentioned that albedo affects how much light gets reflected. So what happens if instead of reflecting light uniformly, we like only decide to reflect the red color? What do you think is going to happen to our surface now? I believe you are correct. I believe ray tracing does predate rasterization. So if we only reflect the red light, you notice that our Glinda is now red. So the sphere now has a red tint because we're not reflecting any of the blue light or the green light that hits us. So all the light that actually appears to us, everything that makes it to our camera eye, is going to be red. Also, you can kind of tell it's hard to see with the graininess. So let's do a really long render. Let's do like 1024 samples. It's going to take a second. A really long second. But you can kind of sort of almost see that we're getting a subtle amount of red reflected around the red sphere on the big gray sphere. I could compiling with optimizations in this situation, I believe, is going to take longer. Oh, I could compile with optimizations. Never mind. Ignore what I just said. What I just said is stupid. Editor, I'd like to scratch that comment from the record, please. Honestly, actually, though, you're right. We should compile with optimizations. Isn't it crazy how much faster it's going? It's insane, bro. Oh, but it also crashed. Well, that's cool. Everything is fine. There is no scuff here. I'm not going to take the time to debug why it crashes in release mode. We're just going to be slow and hope that it doesn't also crash when it hits 111 in debug mode. Oh, what might actually be happening there is we do have a little problem here. Let's see if it crashes. We do have a little problem here where if the random vector, right? So if this is very close to like -1, so if the length, so if our Lambertian direction dot length squared is like really short, it's like less than 0.1, if it's very close to 0, we get problems, like a crash. So what we're going to do is if the length is very short, so like close to 0.01, we're just going to use the normal direction. So Lambertian direction equals our hit normal. And that ideally should no longer crash. I hope. I hate everything. Why is it actually crashing? I also love doing a live demo and not having this problem when we ran normally. And now that we're live, we're getting a random crash. That's the best feeling in the whole wide world. It may also be worth our time just as a check. It shouldn't be necessary, but to normalize the direction. We're crashing in from Cindy. Cannot access memory. Hit sphere, hit pause, out. T equals 0. Yeah, I think our normal is just getting really small. And I'm assuming that that's causing us problems because that number is really close to 0. So I'm assuming that this is a multiply by 0 problem. Which, if we just make sure that our directions are normalized, will hopefully fix it. There is no scuff in the production of this stream. I'm very sad right now. As a slight check, a sanity check, we're also going to throw this little sample from the working demo code that I have in here. And we're going to see if that fixes our problem. We're getting a memory access issue. But we just have just a few less samples and it seems to be working. So we can see that there is red being reflected around. Will it compile with 10 samples? The 10 samples should start to blend out and get some of the red blending in. I know where the error point is. It's in the math library. I don't understand what the problem is, and I'm not going to take the time in this lecture to figure it out. So we're just going to make the number smaller and we're going to continue on. And I believe none of these should be necessary. Okay. So that's a diffuse material. What happens? My own math library, yes. What happens if instead of having a diffuse material, we want to have a metal? How do metals work differently than diffuse materials? Well, in a metal, we don't have this random behavior much anymore. We're gonna put an asterisk on that much. Instead, what happens is we have our surface and we have our normal, right? And then our incoming light is going to just reflect around the surface normal. So if you recall, we have the reflect function, right? Which is v minus 2 dot v with n times n. So we take our vector, we subtract off 2 times the dot product of v with the normal vector and multiply by the normal vector. And that should give us the reflection along the normal vector. If you don't believe me, go check the math video from earlier. There's a whole video on the channel where we prove, as part of what happens, that is the correct formula for reflection. The other thing, though, is we might add a little bit of randomness. So what we're going to do is we're going to add a fuzz / roughness value. And what this does is we're going to have, say that this is a 0.1 sized roughness. We're going to make a little sphere of size 0.1. So R equals 0.1. And we're going to randomly add on a vector in there. So when fuzz is 0, we're going to have perfect metal reflections. But when fuzz goes to 1, right, we almost wind up with like a diffuse type reflection. And that just determines how perfect the reflections are. Fuzz really close to 0 creates something that looks like a mirror, whereas fuzz really close to 1 creates like a really grimy surface that's almost diffuse. So the way we do that, we have vec3 metal direction equals the reflection. So STENMath reflect of the incoming, which is, where did we put the camera? Camera center is at 0, 0, 0. So 0.3 camera equals 0, 0, 0, which means that vec3 incoming equals, wait, no. Yeah, which means that incoming is equal to hit point minus camera, hit pause minus camera. But we can simplify, since we know that the camera happens to be at 0 right now, just to the hit position. So we're going to reflect our incoming direction along the hit normal. But we are going to make sure that we normalize this value. Did I not copy across reflect? Oh. The problem here is that we haven't updated the math library recently. We're going to cd into STED math, and we're going to get polarity base. Get add dot, get stash, get polarity base. Get checkout main, get polarity base. And that should pull down the new vector that does have reflect. Cool. How does research in computer science coding work? I'm not sure how exactly to answer that question. Your question's a little too broad. Could you ask a more specific question, possibly? So we have our metal direction. And now that we have this metal direction, we're going to have a float fuzz, which we're just going to put here for now. We're going to move it out into the hit record in a second, which we're going to set to like 0.1, kind of a small fuzz. And we're just going to add a random unit vector multiplied by fuzz. So if we instead shoot off the ray in the Lambertian direction, we should get nice, crisp, everything's on fire. Just delete build and have the system refix itself. Because I believe I have the fix for that put in the build system now. There we go. We should have a nice What did you do? That's weird. Oh. Oh, it's... okay. Okay, this is fine. So, we should now have... Oh, it would also help if I... This is such a scuffed stream at the moment. If we actually update the metal direction, we crash again. We wind up with this material that acts like a mirror, right? So we can kind of see the dark gray sphere reflected in the big red sphere, right? Pretty much similar to mathematics. You make an assumption, then prove it, because in the end, computer science is mostly just math. Like a PhD person in biochemistry is researching a specific biochemicals and their effects. So what do we do in CS? I don't know. Is your Glinda shiny enough for you? So the one asterisk I will say, Bigger Ben, is computer science is often an engineering discipline, and research in engineering is a little bit different than research in science. Because research in engineering does two things. What you did is scientific research, which engineers also do. But then there's also engineering research, which is basically, I built a thing. I'm going to compare my thing to a bunch of other things to argue that it's better. So half of computer science research is, here's some assumption that I proved. And the other half is my assumption is that my thing is better. So there's the theoretical mathematical type, and then there's the practical, I implemented a thing, here's how it's better type. And in our lab, we call the first one scientific papers, and we call the second engineering papers. And there's lots of sub-branches of computer science. Like the hopping ones right now are AI, so trying to come up with new algorithms to make AI better in some specific way. Quantum computing, trying to make quantum qubits actually usable and small enough to be used and not have to be at like absolute 0 to work. Yeah. Are we ever gonna get rid of the grain textures? To get rid of the grain textures, you up the sample count. But there is a bug with the higher samples that's causing crashes. So we're not doing that. So the last thing that we're going to talk about, we're going to do real fast, is we're going to go into the hit info, and we're going to add a bool is metal, and we're going to add a float fuzz. So now what we can do is in our scene, and we're going to set this to false and this to 0, is in our scene, we can go out is metal equals true, and then out fuzz equals something like 0.1. And now we have our Lambert direction and our metal direction, and we can go vec3 direction equals hit is metal, and we can use the metal direction. Otherwise, we can use the Lambertian direction, and then we can use direction. So we now have two very simple BRDFs. Both of them basically apply a constant, right? With this one, the constant that we're applying is just the color. And with this one, what we're basically saying is for every direction that's not the reflection direction, it's 0. And in the reflection direction, it's constant. So if we formalize that a little bit, let's delete that. The BRDF for diffuse is just albedo. So what that says is for every direction in the sphere, we just multiply it by albedo. Okay? It's just a constant. And since the probability is just this one value, we can sample any probability randomly. We mentioned, right, that the rendering equation is unsolvable. We can only approximate it. And the way that a ray tracer approximates it is by samples. So since every ray that we shoot can take a random path, we're going to wind up getting a couple of different samples of the BRDF. And so the more samples you take, the better an approximation of the rendering equation you get, but also the longer it takes. And then our BRDF metal is a piecewise defined function where the reflection is 0. Actually is, we'll say it this way, is albedo if the incoming light direction is the reflect across the normal of the outgoing light direction, and 0 otherwise. So our probability is 0 that there's any light if it's not the reflection, and the albedo otherwise. And these two BRDFs give us already pretty okay looking surfaces. That was all I had prepped for today, unfortunately. Today was a really short finish-up lecture to the previous ray tracing lecture we did, with a lot more stuff added. So I guess since I have about 15 more minutes, before I have to move on to other things, we can see if we can debug that problem, that memory problem, and see if we can get some higher sample counts. What's next dream about? It's either going to be finishing the window class that we implemented, or it's going to be starting model loading. I haven't decided yet. Okay, so we're failing in from SIMD. Cannot access memory. Not access the SIMD. Huh. So we cannot access the SIMD. So then this is divide. I wonder if it would be better to pull this temporary SIMD out. Actually, not the SIMD, the vector. We pull this temporary vector out, and then we divide by temp dot to SIMD. I wonder if that'll do anything for us. Because I don't think we should be running into any stack overflow issues. If we manage to fix this bug, we should get to see Shining Glinda without the sampling artifacts. Or with less sampling artifacts. Less noticeable sampling artifacts. We still can't access the SIMD. Oh, I'm dumb. Am I dumb? I'm dumb. The problem is that we are running out of stack space. Because we should have a size t depth equals 0 here. And then if the depth is bigger than like 64, then we're just going to return black. And every time we call ray color, we're going to give it depth plus 1. We are stack overflowing. That's the problem we're hitting. It's not a math problem. It's a me problem. It's an implementation problem. So let's go 256. And let's up the switch to release. Give it a run. And we should get a really nice Glinda. Good evening, Marianne. How are you doing? Let's hope that we get something nice. No, my throat's just always fucked. You've been trying to learn Zig and I'm failing miserably? Does it have anything to do with the fact that they just had a big update and it changed a lot of their APIs? Some of my students last semester were using Zig. And like right in the middle of the semester, Zig had a big breaking update and it screwed them over really bad. Like all of the materials stopped being relevant. So I don't know if that's what you're running into. All of the learning materials haven't updated. I don't know if they have by now, but that might be something to think about. Of course, this is a second-hand report, right? Because I wasn't the one suffering through learning materials, so maybe they just weren't looking hard enough or something, but Maybe that helps. And like I was saying, right, the more samples we give this, right, the better of an approximation of the actual rendering equation this becomes, and the less all of these artifacts go away. And if we switch the sphere, I Glinda back to being a diffuse object, we should see a much more pronounced red glow on the big ground sphere. You just took a screenshot of Glinda like this? You want me to upload a picture of Glinda to the Discord? And it's like very subtle, but you can see the reddish glow around the sphere. If we wanted, we could go color F emission equals black. And we could add emission. So hit emission to our array. And we can make our array generate some light. So emission, maybe 1. I don't know how the units are going to work out on this, so I have no idea if 1's going to be super strong or not. This is ray tracing. I won't even pretend that I know enough math to understand what's going on here. Well, if you watch the video that I'm going to edit from the stream, and it should come out hopefully sometime this week or upcoming weekend. I believe I explained most of the math pretty clearly. If you're at all curious, Mr. Myriad. An emission of 1 doesn't seem to have done very much. How about an emission of 100? Are we gonna blow the scene out with red light now? Oh, I wonder if no, it shouldn't. Because that value is, I wonder if the emission value is going to be relative to the pixel count. That would be kind of unfortunate. Did I make a dumb mistake somewhere? Oh, I made a dumb mistake somewhere. Good job. Turns out that first order of business, pluses are not good. Second order of business, a plus there. Third order of business, we are averaging over the, this is going, no, this should be fine. Because there should be a constant that gets added on like every pixel, and then we should divide it away. What made you choose C++ as your language for most things? I just get really annoyed by the syntax of the standard library functions. It's beautiful, chat. We've created a masterpiece. Aye. What made me choose C++? The university that I went to taught it. Actually, that's not necessarily fair either. Because if you're working in games, like low-level games, if you're working in like game design, right? you're probably using C#. If you're working in game development or like engine dev, you're using C++. C++ is the industry standard language for anything that requires performance. Because people haven't fully bought into Rust yet, and Rust is the only like valid competitor that's mature enough at this point. Like Zig isn't a valid competitor because they still do breaking changes to their API like once a year. Whereas I think Rust's breaking changes are much smaller. What did I mess up here? The default emission value is 0, yeah? Yeah. You like Linda? Wow. I see how it is. AI knows when it's been insulted. There we go. So now it looks like the sphere is emitting a little bit of light. We can see the light glowing around it. The only really painful part of C++ for me are build systems. CMake is the bane of my existence. You're self-taught in Rust and currently in your first semester at university. Nice. Linda looks evil in that glow. Okay, shall we make her glow like a blue color instead? So then she's less evil? We'll make her be red, but glow blue, and this will be an interesting look. I kind of agree. CMake becomes so what I'd recommend, modern CMake. There's this, should I call it a book or a blog or this? There's this. The GitLab Modern CMake. Oh, I guess it's a PDF. So we're gonna call it a book. That explains a lot of like nice, decent CMake practices. And if you read through this, like a lot of the really confusing stuff, it will make sense. And I think CMake will be better for you after that. At least as long even if you do flag checking and stuff in CMake, it's not too bad once you get the hang of it, I don't think. The thing about CMake that sucks, though, is cross-compiling to different platforms, and that is where Zig becomes really nice. Never even learned CMake? You should probably learn CMake. It's the industry standard. If you're going to be writing C code, or C or C++ code, it's the industry standard. What does the blue glow Glinda look like? That better, battery? So now let's really crank Glinda. Let's make her like 100 times brighter, and we're gonna see what this looks like. It's gonna like destroy the scene, I'm pretty sure. My hope is that LLMs will get good enough to write CMake files for me. But like, for a simple project like this, right? Why do I need an AI to write this for me? And nothing is that hard, right? I just tell CMake to include this other directory. I add an executable. I link the library to that. I say that I'm using C++ 26. And then this stuff is like copy paste between all of them. Oh boy, look at all those artifacts, chat. Because I think CMake files are easier to write than make files. Well, I will upload the no emission version of Glinda, and we're gonna crank the samples, 1024, and I'll post this in the Discord for Mr. Battery to appreciate. Just because of Glinda, you will learn ray tracing? Well, if it makes you feel any better, hopefully by the end of the week there will be a video. That makes things easier. Cross-compiling is compiling on different platforms. Oh, you mean compiling on different... Wait. CMake does make compiling on different platforms easier, yes. CMake does not make cross-compiling easier. Especially since Windows doesn't like makefiles. Visual Studio won't consume a makefile like it will a CMake file. Can I make CMake video? I've snuck the basics of CMake into a couple of videos, I believe. I suspect that this short, the hello world. Now, yeah, this hello, I should label this better. And some tags to indicate that it talks about CMake. What's called a kit. So we can select, so we'll pick that we're going to use AMD64. We can click this little run button down here. Oh, maybe, maybe I should just do a video where we talk about CMake. And we talk about like subdirectories and libraries and all that stuff in like one place. I'll need to like put together like a sample for that though. Like I'll need to spend some time figuring out like what we build in that. But that might not be a bad idea. I'm gonna noodle on that for a little while. I agree. In the ray tracing video, one of the shorts that's gonna come out of the ray tracing video is how to use subdirectories in CMake 2. Yeah. I should do a CMake video. Oh, actually, does this one? So, we're also then going to need to load up glfw, and we're going to add a subdirectory, third party /glfw. So, we're going to start off by telling CMake, hey, I'd like to load all the code for GLFW in. And then we're also I should also tag this video. Also this video. As I die. Anyways. AI is going to disappear now. Thank you everybody so much for watching, and bye-bye.